Hello, bonjour, merhaba, assalamu alaikum. Welcome to the third week of Statistical Mechanics, Algorithms and Computations from the Physics Department of École Normale Supérieure. Last week, we discussed how the statistical approach provided an exact description for physical systems. As you found out by yourself in homework session 2, this statistical approach captures the system even for finite number of particles. The equivalence between Newton and Boltzmann is one of the great miracles of the natural sciences. It is also a breakthrough in mathematics because there are now mathematical theorems that back up our numerical findings, at least for hard sphere systems. This week, we will study phenomena in the physics of liquids. And this object will accompany us, a giant clothespin that resembles the object that many people use to hang up their clothes. For us, believe it or not, it will be the key for deep insights into physics. We place a first one randomly on a washing line between two poles, like this. Then a second one, like this. And a third one, like this. And so on, until n clothespins have been placed onto the line. Each arrangement of n clothespins is equally likely. And we use the tabula rasa rule to wipe out a configuration that presents an overlap. What is the probability for a pin to be at position x? This simple question will get us to the heart of liquid and soft matter physics. We will discover that although apparently the pin positions are independent, pins in fact experience a strong force. A force that can be seen in neutron scattering experiments or in X-ray diffraction, and that can be measured. This famous interaction was discovered by Asakura and Ozawa in 1954. And it is so important that some people take it to be the fifth force in nature. In this week's lecture, we will study this interaction. It comes out of nowhere, and it exists even though there are no charges, no currents, no mechanical strings. This is why it is called an entropic interaction. It can be so strong that it introduces phase transitions from the liquid to the solid. The clothespin model corresponds to one-dimensional hard disks. In this week's tutorial, tutorial 3, we will study an ingenious algorithm that allows to sample assemblies of tens, hundreds, thousands, even millions of clothespins on a line. Remember, last week we had trouble simulating 4 hard disks in a square. This week we can study so large systems that we can even approach the infinite system limit, the thermodynamic limit. As we will see several times in this course, the great algorithmic success, the fact that we can directly sample thousands and millions of particles without rejections, is mirrored by the fact that we can solve this model analytically. This is what we will do in the tutorial of this week. The analytic solution will allow us to drive home essential messages about liquids and solids, and about the phase transitions between them. The providential Monte Carlo algorithm that we alluded to works only in one dimension. In 2 dimensions and higher, for hard disks or hard spheres, we must resort to the tools of last week: Markov chain Monte Carlo algorithms or molecular dynamics. At small densities, everybody understands that a system of hard disks or spheres is a liquid. But will it solidify at higher density? This is a question that has motivated some of the best work in computational physics. And it has also brought about the revolution in numerical algorithms, in Monte Carlo, and in molecular dynamics. In this week's homework session, we will retrace these classic papers. Our algorithms and our very simple Python implementation are just good enough to get a flavor of what is going on in the system and to observe our first phase transition. So let's get started with week 3 of statistical mechanics, algorithms, and computations. We take up the random clothespin model and place pins on positions x0, x1, x2, and so on, as shown in this program. Each time we check for the distances of the new pin with all the pins already present. And if one of these distances is below 2 sigma, we have an overlap and we reject the configuration through the tabula rasa rule. This is what allows us to sample configurations x0 until xn-1 with a probability pi equals to a constant if the configuration is legal and 0 if it is illegal. As we are on a line that is in 1 dimension, it is more efficient to sample the positions x0, x1, x2, x3, and so on, than to sort them such that x0 is smaller than x1, smaller than x2, and so on, and then check only the n-1 overlaps between neighboring pins. So we check for the distance between x1 and x0, x2 and x1, x3 and x2, and so on. This is written up in the program directpins improve.py. Output of this program for 5 pins of radius sigma equals to 0.075 on a line of length 1, that is with 75% of the line occupied by clothespins, is shown here. Each line shows an accepted configuration with the 5 positions x of the centers of the clothespin. It has taken about 500 trials each time to get one accepted configuration. As we discussed, for n equals to 5, we'll have one acceptance out of about 500. For n equals 10, it will be really interesting. You'll see that the rejection rate will be so high that you accept only 1 out of 500,000 samples. Output will be really interesting for n equals to 15. But don't try to obtain it with this algorithm. You will accept only one configuration, one legal configuration, out of 500 million trials. Wait until Michael, in this week's tutorial, shows you how to sample this configuration for any n, as you like, hundreds, thousands, and millions, or any density without any effort. Output of this program, direct pins non-reject.py, is shown here for n equals 15. Again, you see the 15x positions in an ordered way for all the legal configurations that we obtained. Now, let us analyze these data. And the way to do it is to do a histogram of all the x positions in this table. This is shown here. Look in what a paradoxical situation we are. We placed our pins uniformly on the interval, yet the distribution is oscillatory. Many people, everybody, finds this outcome counterintuitive and difficult to understand. How can it be that close to the poles we have 4 to 5 times more particles than in the center? The poles actually attract the particles. Furthermore, what you see here is not a mere boundary effect. Particles also attract each other, even though this is more difficult to see. What we see here, the attraction of particles through a wall, or the attraction of particles with each other, is what Asakura and Ozawa found in 1954 in their famous paper. And this is what we will study in a moment. Before doing so, please take a moment to download, run and modify the 2 programs we discussed in this section. On the Coursera website, you'll find the program directpins.py that generates random configurations of n clothespins using the tabula rasa rule. Please check out also the program directpinsimprove.py that uses the sorting trick. And please be patient for the direct sampling algorithm without rejections, the directpins no-reject.py that we will discuss in this week's tutorial. When drawing configurations of pins, we must realize that there are 2 types of excluded region. The first type is the core, the space occupied by the pin itself. No other particle can penetrate into this core. But we must realize that the position of the pin is given by its center. And this creates a second type of excluded region that we call the halo. The center of another particle can penetrate neither into the halo nor into the core. The poles also have a halo of size sigma, because all pins must be at x larger than sigma and smaller than L minus sigma. The total core area of our n pins is fixed. It is equal to 2n sigma. The total area of the halos is not fixed. If we put the pin into the center, far from the poles, the total halo area is equal to 4 sigma. If we put the pin to one of the poles, the total halo area is equal to 2 sigma. It follows that the configuration on the right has more accessible space for other particles to be put, and a smaller chance to undergo a tabula rasa wipeout. This means that the configuration to the right has a higher probability than the configuration to the left, or that the particle is attracted to the boundaries. We can also say that there is a force between the boundary and the pin. Let us now see for ourselves whether the halo picture predicts interactions between particles. We will consider a line of length L with a pole to the left and a pole to the right, and two pins with radius sigma, which means core area 2 sigma. Question 1. What is the available space for other particles if we place our two pins far from each other and far from the poles? Answer. For two pins that are far from each other and far from the poles, the available space for other particles is equal to L minus 10 sigma, as you can see from this figure. Question 2. What is the available space for other particles if we place the two pins close together but far from the poles? Answer. The available space for the other particles is equal to L minus 8 sigma, as you see in this figure. Third question. What is the available space for the other particles if we put one pin close to the left pole and another pin close to the right pole? Answer. The available space for the other particles is equal to L minus 6 sigma, as you see here. Final question. The halo picture, can it fully describe the density profile that we obtained earlier? The answer is no. The halo picture nicely describes the increase of density close to the boundaries, but it cannot account for the intricate oscillations of the profile. Please be patient for this week's tutorial, where we will derive an analytical formula which exactly describes this density profile that we obtained from numerical simulations. The halo picture, although it is approximate, applies in any dimension. And it explains why in homework session 2, last week's homework, you obtained an inhomogeneous density profile for the 4 hard disks in a box. For a disk of radius sigma, there is a ring of radius sigma that forms the halo. No other center of a disk can penetrate into the halo or the core area. But notice that a halo itself can penetrate into another halo or into another core area. Isn't that curious? Here on the screen you see 3 configurations of 2 disks in a box. In configuration C, the 2 disks are in the corners, and the available space for other particles is much larger than for configuration B. But configuration A has the least accessible space for other particles. If we have 2 particles already in configuration C, that means in the corners, we have much more available space for the other particles and a lower chance to undergo a tabula rasa wipeout. This means we expect a higher densities in the corner of the box than in the center. And this is exactly what you observed in last week's homework. But you probably concluded that these inhomogeneities were a boundary effect. This misses the main point. Consider the configuration B, the two particles attract each other. In the one-dimensional clothespin model, the oscillations that you see here decay exponentially on the scale of a few clothespins. This means that the boundary effects and the pair correlations decay on the scale of a few sigma. And this implies that the Asakura-Ozawa interaction leads to local modulation of densities and pair correlations. On long length scales, the system is completely homogeneous. And this is what defines the liquid state. The clothespins model is an example of a very general class of physical systems with short-range interactions. Powerful mathematical theorems exclude the possibility of a phase transition in these systems in one spatial dimension. The question is now whether these interactions that we discussed can be strong enough in 2 and higher dimensions to be seen on arbitrary length scales, and whether they can introduce phase transitions. This will be the subject of the next section and also of this week's homework session. In this week's tutorial, we will continue our detailed study of the random clothespin model. But here, let me put what we have done in the lecture and what we will do in the tutorial into a wider perspective. And I will start from a discussion of the two extremes, the closed packed limit and the dilute system, considering systems with periodic boundary conditions. In a one-dimensional system, for random clothespins, the closed packed limit eta equals to 1 is special. We have one pin at x0, then another one at x0 plus 2 sigma, plus 4 sigma, plus 6 sigma, and so on. Even though, because of the periodic boundary conditions, we do not know the value of x0. We have positional long-range order in this system. But we also know, in fact, we will prove in tutorial 3, that for all densities lower than eta equals to 1, the system is different. It is liquid-like, like it is in the very low density limit. In 2 dimensions, that means for systems of hard disks, the closed packed density is equal to pi over 2 square root of 3. And this is about 0.907. And the close packing configuration is hexagonal, as shown here in the picture. The mathematician Laszlo Fejes-Tott proved in 1940 that no other configuration than the hexagonal packing exists at this density pi over 2 square root of 3. So we are sure to have long-range positional and orientational order in this system at the closed packing density. There are no other mathematical results about this system besides the fact that at very small density the system is liquid. To find out what is going on at intermediate densities, we have to resort to numerical simulation. Markov chain Monte Carlo simulations and molecular dynamics simulations allow us to sample these things. For example, here you see a system of 256 disks at density 0.48 again with periodic boundary conditions in X and in Y. Here, the Asakura-Ozawa depletion interaction is at work, and it produces some unconnected local arrangements of disks that resemble the close packing limit at density 0.907. Look at the highlighted spots in the picture. At higher density, look here, the system all of a sudden changes. What you see here on the right is qualitatively different from the configuration on the left. A phase transition has taken place. The discovery of this phase transition from the configuration on the left, the liquid one, to a denser phase, is a computational fact, a computational achievement, and it has also been observed in many experiments. But it is not backed by mathematical theorems. This transition at a finite density below close packing takes place in 2 dimensions, but also in 3 dimensions for hard spheres. The existence of such a transition was first suggested in theoretical works by Kirkwood and Monroe in 1941. In conclusion, please note that in Lecture 3 of Statistical Mechanics, Algorithm and Computations, we have remained within the tight conceptual framework of the equal probability principle. What a simple principle, but what far-reaching consequences and rich and surprising phenomena. And what a nice interplay between algorithms and theory. In coming weeks, we will continue to develop the conceptual frameworks, the consequences, and the algorithms. I hope to keep up your interest in statistical mechanics, algorithms, and computations. In the meantime, let me thank you for listening.